Distance learning lessons. Today we are going to be looking at concave lenses as well as magnification. At the end of this video as well, there is also a little bit of extra work for those of you who are doing triple or higher physics. Let's get started first of all with our knowledge retrieval. There are going to be 4 questions. I'd like you to pause the screen and take 5 minutes to do these knowledge retrieval questions. Okay, so there are your 4 questions. Pause the screen now and attempt to do the knowledge retrieval. Okay, let's take a look at these answers. Remember to mark them with your green pens, please, year 10. Question 1 says, what does it mean if light rays that pass through a convex lens are converging? Well, remember, if we've got something that is converging, it means that the light rays will meet at a point, and that point is called the principal focus. Question number 2 asks you to draw the symbol for a convex lens in a ray diagram. So we knew that a convex lens in reality looks like a tear almost, okay? So it's kind of got that tear shape where it's skinnier at the top and bottom compared to the middle. If we're drawing a ray diagram though, you can have a look at the bottom and you can see that in a ray diagram we draw it like so. Okay, so it's essentially a line with an arrowhead at the top and the bottom. Question 3 asks, what does it mean if an image is diminished, I can never say that word properly. If an object is diminished, it means that it is smaller than the object, okay? So that the image is diminished, it's smaller than the object that was originally projected through the lens. And then finally, question 4 says, an object is placed at a distance between 2f and f away from a convex lens as shown in the diagram. So you can see here that we've got our object in blue and it's between 2f and f away from our lens. How would you describe the image produced? Well, we looked at these last time, so you can either have remembered exactly what those objects would look like, or you could draw on to your diagram to see exactly what kind of image would be produced. So I know that the image is going to be real because it's going to be formed where the light rays actually converge. I know it's going to be inverted and I know it's going to be magnified. And I can show you that this is the case if we draw onto our diagram and follow the rules. Okay, so it's going to be a bit wonky because I'm not actually using a ruler for this. You should use a ruler when you do something like this, but we need to pass through the origin there. Like so, and then our second line would go parallel till it met the lens, and then it's going to pass through the focus point, remember, or the focal point. Let's say it's there, and we continue that on. You can see that that's actually going to continue off my screen, so you can see definitely that when the image does form, it will probably be somewhere around here. It will be upside down, so it's inverted, and it's much bigger than that original object was as well. Okay, so today we are talking about concave lenses, okay? So concave lenses also get called diverging lenses, and that's because of what happens when light passes through a concave lens. When light passes through this kind of lens, it again refracts, okay? So let's draw a couple of light pathways or light rays here. Here's my light incoming onto my lens. It's going to refract as it passes through the lens. And then it's going to refract again once it comes out the other side of the lens, but this time it's going to refract something like that. Again, oncoming into the lens here. In the middle of the lens, it's actually not going to refract. It's going to pass straight through, like so. And if we add our third ray, again, it's going to refract, like so. Okay, so the reason that it's called a diverged lens is because all of these light rays coming out the other side of the lens will never actually meet, okay? They are spread out by the lens, and that is what we call diverging. You can always spot a concave lens because it is thinner in the middle than it is at the top and the bottom. It looks a little bit more like an apple core, okay? So you can think of convex lenses as a tear shape and concave lenses as an apple core. Now, what we'd have to do here is we can see it's very similar to our convex lens that we would previously have used for a magnifying glass. Because these rays on the right hand side of our lens are never going to meet one another, we actually can't use that to produce a real image. We can only ever produce virtual images with concave lenses. And we do that by tracing back our projected rays of light from the right hand side. Okay, so we trace them back like so. And the point at which they meet, i.e. where the rays of light appear to have come from, is where our virtual image will be formed. You can see on the right hand side here that this is what a diagram of a concave lens would look like if we were drawing a ray diagram with it. So we've now met our concave and convex lenses. What I'd like you to do is we're going to start thinking about some uses of lenses, because this is kind of where your exam questions will come on to. So convex lenses have multiple uses. We normally see something like a convex lens being used for a human eye or a camera. We've got it used as a projector or a magnifying glass. Okay, and each different ray diagram that we've looked at last lesson actually corresponds to one of these different types of uses. So, for example, the human eye or a camera, normally you will have your object placed between f and 2f for a human eye or camera, although actually you can have them pretty much anywhere, because the whole point of the camera or the human eye is that you can kind of have those lenses moving in and out slightly depending on where the object is placed and the amount of light that is hitting the object. Okay, so if we think about a camera, if you zoom in on a camera, then typically what happens is the lens moves from the camera either forwards or backwards, and that's determining how far the object is placed away from the film inside the camera or the screen inside the camera, and how big that image will actually appear on the camera screen or in the picture once you've taken it. A projector is very similar to what we've just seen in our knowledge retrieval, okay? So we have our object placed between f and 2f because we want to magnify it, okay? If we're projecting something onto a screen, like a film, we obviously want it to be bigger than the actual object, and we also want that image to be real because it needs to be shone onto something. Whereas the magnifying glass, that's a little bit more different, okay? That's where we'd see normally an object being placed between f and the lens. And we saw this last lesson. If we have an object placed between f and the lens, we'll end up with a diagram that looks something like this. So let me quickly sketch it out for you. Here's our object. If it passes through here like so, you can see that those rays are never going to meet. You have to trace them back. Okay, we get a virtual image that is upright and larger, and that's exactly what you see if you use a magnifying glass. Okay, so if you've got a magnifying glass at home, you can confirm this. You can look at something underneath it and you just see an enlarged version of that thing, but that image is just essentially a virtual image. It's not actually making anything bigger. It's within the lens where it's a virtual image. And you can also play around with it, because if you hold your magnifying glass close to an object and then move the magnifying glass slightly further away from you, at some point that magnifying glass image is going to invert, okay? So you can play around with that and have a look at the different types of lenses and the different things that focal points and focal lengths actually mean to images. Concave lenses are a little bit more tricky when we come down to narrowing uses. The main thing that I can think of that concave lenses are actually used for are stage lights. Now, obviously, if you've got something like a stage light, so here's my rough drawing of a stage light, okay, so there we go. That's where the light would shine out, and ideally, light shines out of a stage light like so, okay, because we want to flood, we want to flood light everywhere, okay, so it would be the same with a floodlight. They've all got these concave lenses so that they can spread the light out a little bit easier and make that light travel a little bit further. Okay, so we also want to look at magnification when it comes to these images, and this might be something that you've seen already in biology. If you haven't, then you definitely will see it in biology at some point when it comes to looking at objects through a microscope. So, magnification is essentially a measure of the size of an image compared to the size of an object. So it's how different the image size is compared to the actual object size. And we have an equation or a formula that we want to use to determine magnification. And that is the following. Magnification is equal to image height divided by object height. What I like to do is I like to kind of put some symbols towards this, not proper symbols, just shorthand versions. It makes it easier to remember this, or it does for me anyway. I'll call magnification M, and then I call image height HI, and then I call object height HO. And then that way I can remember my equation is M equals high ho, or M equals high over ho. Okay, so that's a way that I like to remember this equation. One important thing to note here, okay, first of all, actually there's two important things to note. First of all, it's a ratio, okay, so magnification does not actually have a unit, okay, so you don't have to worry about putting a unit in for magnification. However, image height and object height obviously will be measured in a unit. Ideally, in fact not ideally, definitely when you are using this equation, make sure that both of those heights are the same unit. You do not want to have different units for the image height and the object height. So make sure that they're both in the same unit. Could be millimeters, could be centimeters, could be meters. Okay, let's take a look at some examples. I'm going to show the examples. I'd like you to copy the examples down into your notes so that you've got a really good revision guide to use these from. If at any point you feel like you know what you need to do, then please just pause the video and get on with it. You can check against what I'm going to show you. Okay, so copy the question down into your notes, and then I'll show you exactly how you'd approach the questions. Okay, so example number 1 says that an object that is 2 centimeters tall forms an image that is 250 centimeters tall. Calculate the magnification. Okay, so first thing, what I'm going to do, I'm going to write down my magnification equation. M equals high over ho. And then I'm going to check the question to make sure that I have everything that I need and that they're in the same unit. So I'm being told that the object height, so HO, is equal to 2 centimeters. And I'm being told that the image height, HI, is 250 centimeters. Those are both in the same unit, so I am free to put those into my equation. Magnification, therefore, is going to be 250 divided by 2, which is equal to 125 times the object height. So magnification is 125. So if you look at a magnifying glass or a microscope, sometimes you will see numbers like this written on them, and that's just telling you how many times it will magnify the object. So in this case, it's 125 times the object height. Let's look at example 2. Okay, An object that is 1.8 metres tall forms an image that is 1.8 centimetres tall. Calculate the magnification of the object. Okay, so again, first thing that I do, write down the equation. That way I know that it's trying to stick into my mind. I'm repeating myself. It's really, really making a case for staying in my long-term memory. Again, I'll read the question and I'll take note of anything that I've been given. And this is the point where I want to make sure that I'm going to swap into different units. Okay, so an object that is 1.8 metres tall. So HO equals 1.8 metres. And HI is 1.8 centimetres. Okay, so this is where I need to decide, do I want to put everything into metres or do I want to put everything into centimetres? I'm going to turn 1.8 metres into 180 centimetres. And once I've got that, I'm going to plug that into my equation. So M is equal to 180. No, it's not. It's 1.8 divided by 180. Plugging that into my calculator, I get that M is equal to 0.01. Now this is important, okay, so we can see that we've actually been given a number here that is less than 1. If your magnification is greater than 1, then your object is magnified. If your magnification is less than 1, then your object is diminished. Okay, so in this instance, our object is actually diminished. It's not magnified at all. It is smaller, or the image is smaller than what the actual object is, which you can tell by reading the information in the question. Final example. It's a little bit of a different example. Let's have a look. A magnifying glass has a magnification of 250 times the original object height. If the image produced by the magnifying glass is 28 centimetres, what is the height of the original object? Again, I start off in exactly the same way as what I previously have started, so I write down my equation. M equals high over ho. And now I'm going to read through the question and see what information I have been given so that I can plug it into that equation. So I've been told that my magnifying glass has a magnification of 250. So M is equal to 250. And I don't have to worry about a unit because remember, magnification is a ratio. I've also been told that the image produced by the magnifying glass is 28 centimetres. The height of the image is 28 centimetres. But I've not been told the height of the object, so that's my unknown. So I'm going to have to solve through this equation to try and find that unknown. So what I do from here is I plug these numbers into my equation that I've already written down. M is equal to 250, which is M, is equal to 28 divided by object height. Now I want the object height to be by itself on top of the equation on the other side. Okay, so to do that, I'm going to have to times both sides through by h naught. Okay, so 250 times by h object height is equal to 28. And then to get HO by itself, I'll divide both sides by 250. So H0 is equal to 28 divided by 250. If I put that into my calculator, I get that the height of the object is equal to 0.112 centimetres. Let's round that to 2 decimal places, 0.11 centimetres. Okay, so quite a small object blown up to quite a large height when we use a magnifying glass. Okay, that should be enough for you to have an attempt at the following questions. So on your sheet of paper, okay, or not the sheet of paper, sorry, but on the document that's been uploaded to the OneDrive, there are 3 questions for you to have a go at. They're also going to appear on the next screen. I'd say pause the video and take maybe 10 minutes to have a go at answering the questions on magnification. And then come back here and we can go through them together. You can green pen them and give yourself a score of 3. Okay, so the following 3 questions, they also appear on your PDF document. So if you wanted to pause the video and look at the piece at the PDF document instead of looking at the video screen, you can do that. But I would say give yourself a good 10 minutes to have a look at these 3 questions and then come back here and I will go through the answers for them. Okay, so let's have a go at going through these answers then. Question 1 says, an object that is 3 millimeters tall forms an image that is 12 millimeters tall. What is the magnification? So magnification is high over whole. Image is 12 meters tall. That means it's 12 millimeters tall. Object is 3 millimeters tall. So magnification is equal to 12 over 3, which is equal to 4. Okay, so the magnification zooms in 4 times. And question 2 says an image formed by a magnifying glass is 75 centimeters tall. If the original object height is 35 millimeters, what is the magnification of the lens? So again, M is equal to high over whole. Image height is 75 centimeters. Object height is 35 millimeters. I want that in centimeters, so that is 3.5 centimeters. Plug those numbers in. Magnification is equal to 75 over 3.5. Putting that into my calculator and get a magnification of 21.4. Okay, so 21.4 is my magnification. And then question number 3, an object is 1.8 meters tall. A projector with a magnification of 4.5 times the object height is used to project the object onto the wall. How tall is the image? Again, magnification is equal to high over whole. HI, I don't know, that's my unknown. HO is 1.8 meters. Magnification is 4.5. So 4.5 is equal to HI over HO, which is 4.5. No, it's not, sorry, 1.8. So to get HI by itself, we have to do 4.5 times by 1.8. That's going to give us HI. So 4.5 times 1.8. HI is 8.1 meters tall. So it'd have to go into quite a large building to be projected. Okay, make sure that you green pen those, correct any mistakes, figure out where it is that you've went wrong. I would say the common places for you to go wrong are either forgetting to convert between millimetres and centimetres or centimetres and millimetres, whichever way that you've decided to go. And then you could have done something like me there where I've just tried to put a different number in for my HO, okay? So I misread my shopping list. Catch yourself out if you've done something like that. But well done for attempting the 3 questions. Okay, so at this point in the video, if you're not doing triple or higher physics, then you can pause it and stop and have a go at the Seneca task that you've been set. Or you can continue watching if you really want to, but this part really does just pertain to those doing triple or higher physics. Okay, I'm just going to show you some examples of, or an example of a question that you might be asked, okay? So it's just a little bit more tricky because it involves doing scale diagram drawings, that kind of thing. And I just wanted to show you what kind of stuff that you could be asked in a slightly longer answer version of these lens questions. So let's have a look at a question. Question says a convex lens produces a magnification of ×2 when it is used to form a real image that is a distance of 8 centimetres from the object. Question A says draw a scale ray diagram to show the formation of this image. B says use your diagram to find the focal length of the lens. And C says describe how the position and height of the image would change if the object is moved gradually towards the focal point of the lens. So I'm going to switch to my visualizer so that we can show you how to do this question. Okay, so the first step here will be to start drawing our scale diagram. So first of all, I want to draw my principal axis. It doesn't really matter how long that axis is, as long as it has at least 8 centimetres in it, because that's the only dimension that I've been told. So I'll just draw it quite long. Okay, so that's my principal axis drawn. And somewhere in the middle, I'm going to draw my lens. It hasn't, yes it has actually, I was going to say it hasn't specified, but it actually has. The question did say a convex lens. So if I just draw my convex lens somewhere here like that, okay, so that's the starting point of my ray diagram. So far I've not done anything from the question apart from drawing my convex lens. Okay, and it says we've got an object that produces an image that is twice as large as what the object is. Okay, so I'm going to start by putting my object on. And again, it doesn't really matter where I'm putting the object right now. It's all about where my image is formed that I actually have to put some information in. But I am going to draw my object height to be 1 centimetre tall. And that is because I obviously want a nice number to double when I'm drawing my image height. Okay, so there's my object and it's 1 centimetre tall. Then the question says that a real image is formed at a distance from 8 centimetres from the object. Okay, so there's my object. A real image is formed, which means that we're going to have it on this side of our lens. And it's 8 centimetres in distance away from my object. So 8 centimetres away is here, and it's twice the height. So I'm going to make that 2 centimetres tall. I've inverted it because I know for a fact that most of the time when we have a real image that is magnified with a convex lens, it will be an inverted image. Okay, then the question, so that's our scale diagram, okay? We could add some labels, and in fact I'm going to, just because that makes it a little bit easier. So my object height, HO, equals 1 centimetre. My image height, HI, is equal to 2 centimetres. And this distance is 8 centimetres. Okay, so there is my scale diagram. Part A is done. There's my 2 marks gained from that. Part B says use your diagram to find the focal length of the lens. Okay, so this is where we're going to have to use our rules that we know about actually constructing these ray diagrams to find the focal length. Okay, so remember the focal length is basically the point at which our object on this side, or sorry, that there is a distance between the lens and this image through which the light ray has passed in order to focus. It's where our converging lens would have a principal focus at. So to do that, because we have one light ray that I would normally draw on a ray diagram that passes through the focal point before it gets to the top of my arrow on the other side, I'm going to draw our parallel line from the top of the arrow to the lens, like so. And then I know that from there, that usually passes through a focal length or a focal point before it hits the arrow head on this side. So the focal length is the point at which our ray crosses over the principal axis, which is this point here. Okay, so that is F. And if we measure it, we find out that for me, that's roughly 1.8 centimetres. Okay, so my focal length of my object, or of my lens, sorry, is 1.8 centimetres. Part C asks us to describe how the position and height of the image would change if the object has moved gradually towards the focal point of the lens. Okay, so what I'm going to do now, I'm going to add on our focal length on the left hand side of the lens as well, because that's how we'd normally have our ray diagram. So I've worked out that it's roughly 1.8 centimetres. So it's roughly there. And the question is saying, if we move the object closer to that focal point, what's going to happen to the image on this side? Okay, so let's just try it out. Okay, let's just pretend that we've got an object that we're moving, let's say here. If we do that, we can see that when it comes through this side, it's going to continue this pathway down here, but we're also going to have this intersection in the middle. So this is where our new object would be formed. And you can see that what happens to the position is that it's moving further away from the lens. Okay, so the distance between the lens and our new image is greater. And we also have a larger image as well. Okay, so the image is magnified. So that's what happens to both the position and the height of the image. So this is an example of what kind of thing you might be asked to do. It could be that you also are asked to find the distance between the object and the lens. You might be asked to put it in terms of focal length. So let's do that. Okay, so for our object in red, I see that it is 5.6 centimetres away from the lens. Okay, so object is 5.6 centimetres from the lens. If focal point of the lens is 1.8 centimetres, in terms of focal lengths, I'm going to have to do 5.6 divided by 1.8. It's roughly 3F away from the lens. Okay, so that's where it's formed in terms of focal length. And that's basically it. Okay, so as long as you can ration the science behind it, okay, and you can reason with the scale diagrams and you can think about them logically, these questions are actually quite nice. And in total, you've probably, I mean, you've seen on the question beforehand that that's a 6-mark question, okay? So that's where you can be picking up quite a lot of marks on these questions in your GCSEs.